So, stellar classification. Last week, I talked a lot about our sun. Now I'm going to generalize a little bit and talk about stars in general. There are a lot of different kinds of stars. A lot of stars, a lot of different types, and one of the ways that humans like to understand things is by sorting them. So we've come up with a way to classify different types of stars. The best way we've come up with to do that is with sorting by spectral type. So, let's think about a star's spectrum. As I said in the last video, stars are a good approximation of a black body. So a star would have a spectrum that looks a lot like a black body curve, something like that. However, there's something else in the mix. Another kind of spectra you may recall me talking about in the past are absorption spectra. And again, I'm going to only go over this briefly for the sake of time. Feel free to go back to a previous video if you need to review. But absorption spectra are when some kind of a continuous spectrum, like something from a light bulb or a star, moves through a cloud of gas, right? And this results in the wavelengths, the colors of light that exactly match possible electron jumps for the atoms in that cloud. Those can get absorbed by the electrons and make the jump happen, but the ones that don't exactly match can't get absorbed by the electrons, and so they just pass through. So the result is like a nice, what looks like mostly a nice, clean, continuous spectrum, but with a few bits taken out. Now if you think about stars, stars are made up of gas, you know, and they have a size. They aren't just a point that light comes out of. In order for light's created in the center of the star, but then it has to move past a lot of gas in the star in order to get out, right? So, a star spectrum will actually not just look like a black body. It looks more like this. It's like a black body with little chunks taken out of it. Little bites. Little dips in what you would expect the black body to look like. These are the absorption spectrum. Each one of these, this is like the result of an absorption spectrum and a black body spectrum being combined together. Each one of these dips corresponds to a electron orbital jump that's possible for the atoms in the star's atmosphere. And so you can use this to learn something about the composition of the star. So this is nice. Now, one line that you might see is the line called hydrogen alpha. Hydrogen alpha is the wavelength. It's a specific color. I think in the ultraviolet somewhere. I'm not exactly sure. I think that's right. But basically, it corresponds to the jump from the first to second electron orbital in a hydrogen atom. It's a very common type of light because of how much hydrogen there is in the universe. There's a lot of it. So, hydrogen alpha kind of gets a special name for that reason. Now, early in the early 1900s, when astronomers were starting to look at the spectra of stars, some people, I think one person, I don't remember his name, came up with a way of classifying stars based on the strength or the depth of their hydrogen alpha line. he said that the stars that had the strongest or deepest hydrogen alpha line were type A, and then the second strongest type were B, C, D, and so on down to, I believe, O, were the categories that he came up with. And this was used for a while as a way of classifying stars. However, a little bit later, also in the early 1900s, but a little later, we had a very famous, very influential astronomer, Annie Jump Cannon. Annie Jump Cannon, excuse me, Annie Jump Cannon thought that the kind of insight that she had was that the strength of the hydrogen alpha line was not really a very important or interesting quality of a star. She thought that it would make more sense to classify stars based on temperature. And she determined stars' temperature based on the location of the peak in their blackbody curve. However, she did find that these categories still kind of applied, and in any case, these were categories that astronomers at the time were already used to. So she used a modified version of this, which is what we still use today. She got rid of a bunch of the letters, because she thought that those categories weren't interesting or significant, and the ones she kept, she rearranged based on temperature, leading to our modern spectral type classification system. O, B, A, F, G,